Hi everybody, welcome to this introductory video on the F distribution. The F test statistic and F sampling distribution are used for inferences about two population variances. That's how they were used in the second section of Chapter 11. They're used in analysis of variance tests. Those are called ANOVA tests, which are the subject of Chapter 13. And they're used in regression analysis, which is in Chapters 14 and 15. So this video introduces the F distribution to a certain extent, to the extent that it needs to be introduced in order for us to use it. The F distribution is a probability distribution, so the area under the curve is 1. It was constructed to give probabilities for ratios of variances. So a ratio is one number versus another number. So F test statistics are always a type of fraction with a numerator on the top and a denominator on the bottom. F distribution test statistics have 2 degrees of freedom, 2 separate degrees of freedom. So every time you use an F test statistic, you're going to have to do 2 degrees of freedom calculations. The numerator degrees of freedom is called DF1. It's called that because it's based on the numerator in the test statistic. So the test statistic always is a ratio, it has a top and a bottom. And this numerator degrees of freedom calculation is always associated with the top of the test statistic in some way. The denominator degrees of freedom is called DF2, and it is based on information from the denominator of the test statistic. So you see sometimes these degrees of freedom called just DF1 and DF2. Sometimes you see them just called numerator degrees of freedom and denominator degrees of freedom, so you should know them both ways. Whenever you see an F distribution being used, you'll always see the 2 degrees of freedom being listed. The F distribution is always positive and it is not symmetrical. So when you draw a generic F distribution, it looks kind of just exactly like chi-square. They always draw it with a vertical axis because it starts at 0 and goes up from there. So that vertical axis signifies the origin. You know, this is 0, 0, the point 0, 0. So along the horizontal axis, you have values of F, and the distribution is above the axis and to the right of 0. So it looks like that. F tests are usually upper-tailed, and we are only going to use them for upper-tailed tests in this class. Therefore, our study of the F distribution will be limited to upper-tailed tests on this handout. For upper-tailed tests, you need upper-tail critical values and you need upper-tail p-values. Where do they come from for the F distribution? The F table contains critical values, the upper-tail critical values. P-values for F tests will be calculated in Excel. The notation we'll be using for the F distribution is given in this table. We have F test statistics. Those will be the letter F with the subscript test to denote that that is a test statistic. F test statistics are always going to be one variance divided by another variance. F at alpha, that's an upper tail critical value of F at an alpha probability level. The critical value in an upper tail test with an F test statistic, that's our notation for it. DF1 is the numerator degrees of freedom, and DF2 is the denominator degrees of freedom. For F distribution problems, the upper tail rejection rules will continue to follow the same patterns that we have learned for Z, T, and chi-square. The only thing we need to learn about the F distribution is how to pull the correct CV and p-value for an upper tail test. So what do I mean by the same patterns? So CV approach, the CV rejection rule for upper tail tests is always this: if the test statistic is greater than or equal to the upper tail CV, reject HO. The p-value rejection rule for upper tail tests is this: if the upper tail p-value is less than or equal to alpha, reject HO. So when we had a Z test statistic, we had to compare it to an upper tail critical value of Z. When we had a Z test statistic, we had to calculate the upper tail p-value from the Z distribution, or look it up on the Z table. For T, it was the same. If the test statistic was T, we had to compare that test statistic to an upper tail T critical value. We had to use the T distribution to calculate the upper tail p-value in that case. So in this way, we are going to expand or continue applying this to the F distribution where our rejection rule for upper tail tests will be if the F test statistic is greater than or equal to the F upper tail critical value, reject HO, and our p-value rejection rule will be if the F upper tail p-value is less than or equal to alpha, we reject HO. So how do we get upper tail critical values and p-values for F? Critical values are going to come from the F table, and p-values are going to come from Excel. Looking at this exercise, consider an upper tail F test at an alpha equals 0.05 significance level with numerator degrees of freedom df equal 25 and denominator degrees of freedom df equal 29. Before I go on to part A, I'm going to modify the notation of this because we know that numerator degrees of freedom are not just df, they're df1. Denominator degrees of freedom are not just df, they're df2. So they're positionally in the right place here, and they're called numerator and denominator, but we can further notate them with df1 and df2. Part A says, what is the critical value you need to decide whether to reject HO? Draw the rejection diagram. So for an upper tail test, using an F test statistic, what you need is an upper tail critical value of F. How do we notate that? With F at alpha. So upper tail critical value is F at alpha. That is F at 0.05. Now, we have numerator degrees of freedom 25, denominator degrees of freedom 29. Critical values come off the F table, so let's go look at the F table. The F table makes you combine information about df1, df2, and alpha in order to find the upper tail critical value. So denominator degrees of freedom are given in this first column. You see there's an extra T there, but it's denominator degrees of freedom. So this set of 4 rows is for 1 denominator degree of freedom. This set of 4 rows is for 2 denominator degrees of freedom. Across the top, we have numerator degrees of freedom. So numerator degrees of freedom are df1. Denominator degrees of freedom are df2. Within each set of 4 rows, looking in the second column, we see area in the upper tail, and that is going to be alpha. So what you're going to do is go into whichever row is for your alpha. Let's apply this to, we had degrees of freedom 1 was 25, degrees of freedom 2 was 29, and alpha was 0.05. So what you want to do is actually flip forward in your F table until you get to the section for degrees of freedom 2, 29, denominator degrees of freedom 29, and then go over to the column for 25, because that's your degrees of freedom 1. So I've arrived here at the last page of the F table. df2 in our problem is 29. df1 in our problem is 25. Alpha is 0.05. So we go across this row and down this column, and we get 1.89. That is the upper tail critical value of F with degrees of freedom 1, 25, degrees of freedom 2, 29, and alpha of 0.05. Now we're asked to draw the rejection diagram. So you saw the generic F distribution that I drew above. Let's draw another one. Vertical axis, horizontal axis. We have the generic F distribution that looks a little bit like chi-square. It has a long upper tail. In an upper tail test, the rejection region is in the upper tail. The boundary of the rejection region is the critical value, 1.89. So we would have to get 1.89 or above in terms of our test statistic in order to reject the null. So that shaded area, that defines our rejection region. So reject HO if the test statistic is greater than 1.89. Part B says, if the test statistic here was F test equals 3.1, what is the p-value? We have a one-pager called Calculating P-Values in Excel. The last distribution listed on it is the F distribution, and the first bullet point shows how to calculate the upper-tailed p-value for an F test statistic. It's analogous to our upper-tail p-values in Excel from other distributions. It's going to be f.dist.rt, open parentheses, you type in your F test statistic, comma, the first degrees of freedom, the numerator degrees of freedom, comma, denominator degrees of freedom, close parentheses, and hit enter. So the upper tail p-value equals f.dist.rt, open parentheses, 3.1, comma, 25, comma, 29. Let's go ahead and calculate that. .0.00199, which to to 4 decimal points rounds to 0.0020. So when doing an upper tail F test, you get your upper tail critical values from the F table, and you get your upper tail p-values from Excel.